So the problem with most robotics courses out there is that they only focus on the math theory. But in this course, we're going to focus on not only the math theory, but also the physical understanding and how to move into simulation. Specifically, we'll be using the UR robot and see our simulation working in ROS2 and Python. This course is broken down into 5 parts. The first part is focused on position and orientation, basically how to describe where your robot is in space. So we'll cover the rotation matrix, the Euler Angles, axis angle, and Quaternions, and end it with transformation matrix. So this sets us up for part 2, which focuses on the kinematics. So first we'll dive into DH parameters, then go into forward kinematics, then inverse kinematics. Part 3, we'll dive into numerical methods. So we'll first explain what the Jacobian is, dive into the numerical version of it, and end it with the inverse kinematics using numerical methods. Part 4, we'll dive into trajectory planning. So we'll go into joint space trajectory, Cartesian space trajectory, talk about singularities, and workspace analysis. And the last part, we will dive into manipulator dynamics, specifically the Newton-Euler method, and finally, the Lagrangian. To follow along the code and doc, see the link in the video description. And if you're new to ROS, I have a 2-hour video on my channel. Go ahead and check it out. And to get the most out of my channel, you could consider checking out my membership. Come here to join and choose the robotics builders for a lot of my behind-the-scene videos. All right, in this video, we're going to talk about what is a rotation matrix, the 3 interpretations, the 3D rotation matrix, and lastly, the rotation matrix operations like multiply, inverse, and transpose. So what is a rotation matrix, the 3 interpretations? So this right here is a 2D example. We have one frame, which we call frame 1 with the curly braces. This is shown using the solid lines. For the x-axis, we have x1 hat and y1 hat. And the second frame, frame 2, this is x2 hat and y2 hat. So the idea is this frame has been rotated by an angle theta. So now the question is, how do you express this rotated frame relative to the original frame? So here we could read it off actually. So this right here, this is the x2. So the x-axis of frame 2, we could express it using sine and cosine. So we have cosine in the x direction, sine in the y direction. Similarly for y2, how do we express that? So right here we have y2. This is going to be negative sine in the x direction, and then we have cosine in the y direction. So when we put it all together, you can see right here, if I move my head, basically I'll slide over so you can see here, but basically you can see this is going to be, this is the x2, and then this right here is going to be my y2. Okay, so these are my 2 axes represented in a matrix form, and this is what we call the rotation matrix. So if I scoot over, you can see right here, this is yet another representation. So these are the column vectors x2 and y2 hat. So you could sometimes see it in this notation R12, meaning going from frame 1 to frame 2. This is the rotation matrix that takes it there. Now, here is the first interpretation that we said, right? So describing a rotated frame 2 relative to frame 1. So this is how we've described this rotation, right? And this is one of the most common ways that we use the rotation matrix for interpretation, especially when we're dealing with different robotic frames that we'll see later on. And right here, you can see this is yet another representation. So this right here, we have a vector. So this vector v1. v1 is originally right here. So this is a 1, 0 vector. And the idea is we want to use this rotation matrix to rotate the vector by some angle theta. So when we take this vector and rotate it, what we want to do is take the rotation matrix, multiply it by the vector, and then this will give us our new vector. So you can see right here, this is our final equation here. So v2 is going to be r times v1. Now to complete this example, you could see we've used actual numbers here. This was the rotation matrix that we've derived. And if we were to multiply it out, our final vector is going to be cosine and sine theta, which agrees with what we got previously. So the second interpretation of the rotation matrix, what we saw right now, is rotating a vector. So when you rotate v1 by theta to get v2, this is the equation that you get. So that's our second interpretation. Now, this third interpretation of the rotation matrix is expressing a vector in another frame. So when you want to express v1 in frame 2, that's another way you can look at it. So here, if we look at our same vector here, it's the same idea. Instead of rotating it, you're just saying, how can we describe this vector in a different frame? Or how do we express v1 in a rotated frame? So it's essentially the same idea. You're rotating a vector, but now you're kind of viewing it from a different frame. Now for the 3D rotation matrix, let's see what that's all about. So if we look here, this is our 2D rotation matrix, which we've derived. The 3D rotation matrix introduces one more component. This one right here is the Z component. So in this specific case, it's going to be 0, 0, 1, because we actually find that the two Z axes for the two frames is actually the same axis. So it's pointing in the same direction. So when it rotates about the Z axis doesn't change. So here's a visual of, this frame being rotated about the z-axis by some angle theta here, okay? So this is going to be the 3D rotation matrix. And you could do the same process to derive the other rotation matrix. So this is the rotation matrix about the x-axis, where the x remains the same, 1, 0, 0. You have the rotation about the y-axis, where the y-axis remains the same. You can see the 1 in the second component. Notice the 1 in the first component here, and then the rotation about the z-axis, which is the one we just saw, where we have the 1 in the third component. So the most generic form of a rotation matrix is going to be this right here, a 3x3 matrix with 3 elements in it. And based on this one of these different forms that we see here, we could identify the type of rotation that we're dealing with. So rotation matrix operations can include different things like multiply, inverse, and transpose, which will be very helpful in many applications. So when you want to rotate about z, y, and then x, you have to pay attention to the order of operations. You first have the z, then the y, and then the x, because the idea is you normally multiply by some vector v here, and you're doing the rotation like this order that you see here. So it goes inwards, then outwards. And of course, the order matters. So when you do Rx times Ry, it's not the same thing as Ry times Rx. And the inverse is a transpose. So this is actually a very nice property of it, which makes the computation very light. So when you want to go between frames, like let's say from frame 1 to frame 2, and you want to go back and forth, you just need to take the transpose of the two rotation matrices. Okay, so we have our UR robot here in RViz, and we're going to have a physical interpretation of the rotation matrix using this model. So first off, what we want to do is figure out how to see the transform. So you can see right here in RViz, right now there's not any transforms showing. So you could come here to the add button. I click down here. You want to search for TF, hit OK. You can see we see all the transforms now. Thing is, it's showing too many, so I just want to suppress all of them. And the only one I want to see right now is the base and the last link. Okay, so if we take a look at this, we can start to have some understanding. You can see the blue axis for the bottom is pointing up, right? And you can see that right here, this is a frame. So if we look at this one at a time, so I'll just open up Paint so I could draw something, but I'll put it by the side here. So just by looking at this, and if we want to represent the transform of the tool end relative to the base, what we want to do is, we could read it off one column at a time, which is how we define the rotation matrix, right? So if we want to see the direction of the x-axis, of the tool with respect to the base frame, what we see here is that this x-axis, which is in green, is pointing in the opposite direction of the base. So what this tells me is I could say this should be -1, and then the other component should be 0, 0. Okay, so that should be the x-axis. And then the y-axis, you can see, is pointing down, and it's going to be the opposite direction of the z-axis. So this tells me it should be 0, 0, -1. And then lastly, the z is pointing in the opposite direction of the y. So if I print that out, it should be in the opposite y. So 0, -1, and 0. Okay, so this would be my expected rotation matrix if I were to describe the tool end relative to the base. Now, if we come back here to our program, what we can do is I've created a node here. So inside my Euler Kinematics, this is just going to print out the tool frame rotation matrix. So basically, if I come here, I have a code here. So let me just first source install setup.bash. And if I run this command, copy and paste this, we should see our transformation matrix outputting. And if I screenshot this, let me see if I screenshot, I'll just choose a rectangle here. And we come back here to our paint. And if I paste this, make this a little bit bigger, you see we have exactly the same rotation matrix, -1, right? You can see everything is lining up. -1, 0, 0. You can see there's some small offset here. This is probably just rounding errors. And then you can see right here, 0, 0, -1, which matches. And then 0, -1, 0. So that matches. So basically this confirms our visual understanding of the transforms here in RViz, and mathematically it matches up. So previously we talked about rotation matrices, but in this video we're going to be covering Euler Angles, specifically the types of Euler Angles, how to use Euler Angles to calculate angles from rotation matrices, and finally end it with the problem of gimbal lock. So all the code and documentation I'm covering will be in the link in the video description. So the idea with Euler Angles is that any orientation can be described with 3 consecutive rotations using Euler Angles. So it's the most intuitive way to describe orientation. So here we have a frame. The red is X, green is Y, and blue is Z. So we're going to go through a series of rotations to see what this means. So if we look here, this is our initial orientation. And if we rotate about the x-axis, you can see it does this rotation. And then if we rotate about the y-axis, the green axis, you can see it does this rotation. And then lastly, it has a rotation about the z-axis. So this does another rotation. So we define 3 different rotations here, x, y, and z. These are the 3 rotations. And after that, you come up with a final rotation from the 3 rotations. So doing the order sequence z, y, x, this comes up with this equation here, rz, ry, rx. And when you take all 3 rotation matrices together and multiply it, then that's how you get your Euler Angles. There's a part 2 to this video later on where I go into deep dive using the UR robot as an example. So it's going to be in the link in the video description. But here is the different types of Euler angles. So first we have what's called the proper Euler angle. So this is where the first and third rotations use the same axes. So these are the different type of combinations. And then we have this Tate-Bryan angles. This is where all 3 axes are different. So notice that all 3 are not the same. And one thing to note is that the order does matter. So XYZ is not going to be the same as ZYX. So you have to be careful when you're looking at the order of operation. So here, this is the rotation. So when we have a rotation matrix, right, if you have the 3 rotation matrices multiplied out, you could expand all of this The C is for cosine and S is for sine, and we have the subscript for the different angles. So when you have this all expanded out after you multiply it in using the symbolic form, you compare it with the general form R using just the 9 components of your rotation matrix. And you could solve for the angle theta using a tan 2 is going to be negative R31, and the square root of R1 squared plus R21 squared. And then psi is going to be a tan 2 of R21, R11, and phi is going to be a tan 2 of R32 and R33. So when you have a series of rotation, there's usually a couple of different ways you might end up here. So you could be given a rotation matrix. So this might be what's given, and then you might be asked to figure out the Euler angles. Or you could have the Euler angles and you're trying to find the final rotation matrix. So you could go between back and forth either way. And there's a problem called gimbal lock. So this is where the second joint is at plus or minus 90 degrees, and you essentially lose 1 degree of freedom. So you might initially have a full 3 degree of freedom gimbal system that you can independently control. But when you have 2 joints lined up, like in this case, then you will lose a degree of freedom. So what this means exactly is you could see in the left image, the 3 axes are all perpendicular. So we have the red one is pointing up, the green one is pointing to the right, and the blue one is in and out of the page, right? So what happens in this right configuration is that the blue and red motors are aligned, so their axes are aligned. So you can imagine if there's an object right above here, if the blue were to rotate or if the red were to rotate, the rotation of those 2 axes would cause the same rotation. So you're not introducing a new degree of freedom. Those 2 are overlapping and essentially causing the same rotation. So this is the concept of gimbal lock, where you lose a degree of freedom. So we have the example in Arvis here from last time, and we've identified the tool frame of the tool end relative to the base. You can see this is our base frame. So let's take a look exactly what this means. Let me just screenshot this so we could have it for reference. I'll open up Paint here and put it next to each other. But if we come back to here, what I have is Euler's angles code right here, and basically it's going to calculate the Euler angles for me. So here we have the rotation matrix and then express it as Euler angles. And we have a command here that we can run. So it's going to be called this one here. I'm going to go ahead and copy this for reference later. I'm just going to paste it here. Okay, so if I run this, I've already built it. But if you run this, you can see this is the output, right? And we could screenshot this so we could double check if this makes sense. So if we come back here, I'm going to paste this and analyze this example here. Okay, so oops, I think I accidentally clicked this thing. Just ignore that. Okay, so if we take a look at the base frame, and one thing to note too is about the order here. So we have multiplication of yaw, pitch, and then roll. So the idea is you might take a frame. Let's see. So you'll have some rotation here, and you want to rotate it by this, rotate it by that, and then rotate it by this. So if we try to draw this frame down here, right, what we have is this is your y-axis, this is your x, and then this is your z. So the initial rotation is yaw. So this yaw here is going to be a 180-degree rotation about the z-axis. So first is 180 about the z. So what this will give me, if I draw a different color, rotation about 180. So this will bring my y-axis here, and then my x-axis this way. I'll call it prime, and then this will be my z prime. So the second rotation is basically 0. There's some rounding error, but you can see there is basically 0 rotation. So essentially my new frame is going to be Z2 prime is going to be the same as that rotated frame. So I'm just going to rewrite it. And then lastly, we have our final rotation. So this rotation is a negative 90-degree rotation about the new x-axis. So here I'll just draw x double prime. So if I have a negative rotation about the x-axis, what we will have is y is going to be pointing down, and then z is going to be pointing this way, and then x is going to be the same. Now, if we compare it, you'll notice that this is, in fact, this exact same frame here. You can see this one is our x triple prime. The x-axis is pointing that way. This is our z triple prime, which is pointing away from the robot tool end. And then pointing down is y triple prime. So we've shown that using the Euler Angles, we were able to go from the base frame all the way to the tool frame using the 3 Euler Angles. So previously we talked about Euler angles. In this video, we're going to talk about axis angle rotation and how to go from rotation matrix to axis angle. I have all the code and documentation for this series, link in the video description. So the axis angle rotation, the idea is you have a rotation of an angle theta about a vector k. So this is the most generic way to represent a rotation. So typically when we talk about rotations about XYZ axis, it's only about 3 fixed axes. But now you have the generalization of rotating about any vector k. And this vector k, we represent it as kx, ky, and kz. So the axis angle rotation, the main idea is sometimes you want to convert it to a rotation matrix. So the idea is you have a vector k and the angle theta. Then you could represent what's called the cross product matrix, where you take the vector k, you put it into this symmetric form. And then you could figure out the rotation matrix by plugging this in. So you have r equals I plus sine theta, the k hat here with the cross product matrix form, plus 1 minus cosine theta, and that same cross product matrix form squared. So this will give you your rotation matrix. And if you want to go from rotation matrix to axis angle, you'll typically have a rotation matrix in this form, some numerical values. And all you have to do is plug it in here to r cosine. You have the trace of the rotation matrix minus 1 divided by 2. And the actual axis is found by 1 divided by 2 times sine of theta. And then you have r32 minus r23, r13 minus r31, r21 minus r12. And in my members video, I go through an example using the UR robot in ROS. So let's go through a concrete example using an axis angle from a 90-degree rotation about the z-axis. So we start off with the RZ formula, the rotation about the z-axis, and we could see this is the formula here, cosine sine, negative sine cosine. So what we want to do is substitute for the angle theta, and we know that cosine of 90 is 0 and sine of 90 is 1. From that, we get this matrix here, 0, negative 1, 0, 1, 0, 0, and 0, 0, 1. So now that we have the formula, we could compute the angle, right? So we have theta equals arc cosine, and we just plug in the r here. So we have the trace, which is 0 plus 1, subtract 1, divide by 2. So arc cosine of 0 is 90. And then the next step, we want to compute the axis. So the k-axis we could get from 1 divided by 2 sine of 90 degrees. And then we plug in the 3 components from our rotation matrices, plug it all in, and then we have 1/2 times 0, 0, 2. And this is going to give us, finally here, 0, 0, 1. So as we expect, the theta equals 90, and we have k of 0, 0, 1, which means it's a z-axis. So it makes sense that we have a rotation about the z-axis from our rotation matrix. Now we can also go the other way. So we could construct the R matrix, assuming we have theta is 90 and K is 0, 0, 1, using the formula here. So if we plug it in, we have our K here is 0, 0, 1. We construct the cross matrix here, cross product matrix, and then we compute it, have it squared. So we're going to get this new matrix here that you can see over here. This is our final matrix after you multiply it out. And then when we go to the next step, what we have here is we just continue our operations, right? We have just plug it into a formula, this matrix plus this plus that. And then finally we get 0, 1, 0, negative 1, 0, 0, and 0, 0, 1. So we could compare with our previous matrix here, right? 0, 1, 0, negative 1, 0, 0, 0, 0, 1. So this matches our expectations. So we were able to go between the axis angle to rotation matrix and then rotation matrix back to axis angle. So I purposely chose a very simple example of a rotation about the z-axis by some angle 90 degrees. Mostly because it's very easy to visualize and interpret the numbers. Okay, so we're ready to talk about the angle axis representation here. So this is going to be the example we're going to be running. We're running this one right here, run Euler Kinematics axis angle rotation. So if we look here, you can see this is our axis angle. I mean, sometimes you'll see it as angle axis. I may have switched it up. But anyway, you can see this is our code here. So basically what we're doing here is we have our rotation dot from Quaternion and then r dot as rotation vec. This is going to give our rotation vector. We have our angle here, take the norm, and then get our axis. So if we go ahead and run this, we could see the printout. So run Euler Kinematics. This is the Euler Angles. This one right here. Axis angle rotation. You can see this is our output. I'm going to screenshot this so we could use it for reference. So if we come back here and we paste it, let's take a look at exactly what this means physically. Okay, so if we look at the base, I'm going to draw the frames if I were looking at it straight on, like at the page. So if we come down here, I'm going to use this brush tool. So I'm going to draw this axis here. This is my x-axis is coming out of the page. Actually, let me draw a little bit higher so it's easier to see. But yeah, so we have our x-axis here coming out of the page. And then this is our y-axis. So by the right-hand rule, our z-axis is pointing up. So this angle axis rotation tells us that the axis is at some vector here in the yz plane. So we have our yz plane, the z part is in the negative direction. So if I were to draw this out, then it tells me that my angle of rotation is somewhere here. So this is my axis. That's represented by this right here. And if I extend this out, it'll look something like that. It's a little bit crooked, but it's okay. So we have the angle of rotation here, which is positive 180. So if we have a positive rotation of 180, it's basically like saying I'm mirroring this y-axis here. So if I mirror this, let me just use a different color. If I mirror this, then this tells me that the new y is going to be pointing down. And the z, if I mirror across here, z will point this way because it's being mirrored across this axis. And then the x-axis, if you mirror it about that axis, it's going to flip so it goes inside the page. So this is our new set of axes here. And if we compare it to the tool end, it actually matches up. So this one right here is our y prime. This is our z prime. And then x by the right-hand rule points into the page. So this is our x prime. So this angle, axis angle representation shows it correctly, and we've verified it by this example right here. So previously we talked about axis angle rotation. In this video, we're going to cover quaternions. So we'll talk about how to go from quaternion from axis angle rotation rotating vector with quaternions, rotation matrix to quaternion, quaternion to rotation matrix, and finally doing interpolation with quaternions. My documentation and some advanced examples will be in the link in the video description. So a quaternion is a four-dimensional number of this form. So you see Q equals W plus XI plus YJ plus ZK. You can also write it as a 4x1 column vector. W is going to be a scalar part, and then the XYZ is the vector part. So it has a special property where I squared equals J squared equals K squared equals IJK, which equals -1. And the quaternion from the axis angle, you could see a rotation by angle theta about the unit axis K. So K is KX, KY, KZ. And it maps to the quaternion. So this is how we could write it. So the same vector we describe, if we want to write it in terms of axis angle, we have cosine of theta divided by 2, kx sine of theta divided by 2, ky, and kz. So what you want to know is that Q and negative Q represent the same rotation, the double cover property. So this is a special property that it has. And we also have an example here. So let's say we have a 90-degree rotation about the x-axis. So theta equals 90 and k equals 100. If we plug it in, this is what we get here, 0.707, 0.70700. So unless you have a very creative or imaginative mind about how to visualize quaternions, most of the time, I like to just interpret the physical meaning from things like axis angle or rotation matrices. And then the quaternion is just four numbers that it outputs, which doesn't really have a lot of physical meaning if you just directly look at this. So some things you could do with the quaternion, though, to a vector is if you want to rotate a vector with a quaternion. So to rotate a vector v using the unit quaternion, you could have p in the form of 0 and v. And you could compute it right here using this notation here. So Q times P times Q to -1. And you could see here that Q to the -1 here is Q star, which is just the XYZ component is the negative part. So for the quaternion multiplication, or also called a Hamilton product, this is what it comes out to be. So once you take the product of everything, you just plug it into this formula. So here's an example. If you want to rotate a vector v equals 100 by 180 degrees about the z-axis. So we have theta equals 180 and k equals 001. 001 because that's the z-axis. So what you want to do is build up the quaternion. You plug it in here, you get 001. So here we have the p vector 0100. And if I move over, you can see the other vector we have here is 000 -1. So if we compute the product here, we have this new vector 0010. And then if we compute the product again using the Q star, if we multiply everything out, and finally the final answer we get is going to be 0 -100. So we have step 4 here. We have this new product here. We multiply that one out. When we do that, we have 0 -100. And then we have P prime is 0, V prime, plug it in here. And then we have V prime is -100. So this is the expected result because when you multiply a vector by 180 degrees, it's the same thing as flipping it. So a 180 rotation about Z flips the x-axis to -x. So this actually makes sense that is -100. Now you might also want to take the rotation matrix to quaternion. So we have this formula here for W, X, Y, and Z. So you pull all the components for the R from the rotation matrix. And if you want to go from quaternion to rotation matrix, then you could take the W, X, Y, Z and plug it into this formula here. If I scoot over, you can see the rest of it. So basically just plug it into this formula and then you should get your rotation matrix from your quaternion. So for spherical linear interpolation or SLIRP, that's one nice property of the quaternion is that when you do interpolation, unlike Euler Angles, sometimes you'll have some discontinuity. With quaternions, it makes it really nice. So you can think of SLIRP as taking two quaternions, Q0, Q1, and some time t, T is some parametric parameter that goes between 0 and 1. Actually, not time, it's just a parametric parameter. And then what you want to do is have Q0 times Q0 inverse times Q1 to the T. And if you expand this out, you can see over here it's going to be sine of 1 minus T omega, or yeah, omega divided by sine omega Q0 plus sine of T omega divided by sine omega times Q1. And what is omega exactly? Omega is going to be this parameter here, arc cosine Q0 times Q1. So you could use this when you're doing some of the kinematics later. If you want to sweep it across two different orientations, you would use this formula right here. Okay, so in this example, we're going to be using the same robot we've been using with the tool end right here. But what we're going to do is analyze the quaternion. So we have a code here. This is our quaternion node. So basically what we're going to be doing is we're going to be reading the quaternion and we're going to print it out. So here we have our print quaternion. So this is going to print it out right here. So this is the Q is going to be pulling it from the rotation, and then also printing out the rotation matrix to compare it. So we can go ahead and run the ROS to run your kinematics quaternion. You can see this is our output. So if we take a look at this, there's a slight rounding error here that we could basically ignore. But we take a look at this. I'm going to go ahead and screenshot this and again, put it side by side. So based on our definition, we know that this is going to be the rotation. So if we look at this from here, basically you could, if I open up a paint, you could see it right here. So it's usually easier to just look at it. But you can see if I screenshot this, I'll put it side by side. If we look at the rotation matrix, what this tells us is that the main component of the x-axis is in the negative x, which is correct. And then the y component is in the negative z. And then the z component is in the negative y. So that all matches up based on some of the previous videos we told us. And this right here, basically you just have to plug it into the formula. So if we look at the quaternion equations that we've had, if we find the rotation matrix, it's good to just go through the exercise here so we could verify this. So I'm just going to copy this and come back to here. So this is our equation. And if you just check a few terms, for example, you could compare it. So for the first term, we see it's 1. And we could plug in, like, for example, let me just go through some of these numbers here. But if I use my brush tool, you can see the first term here is going to be 1 minus 2 times y squared plus z squared, right? And we can see it's 1 minus 2. The y term is 0.707 squared plus the z term is negative 0.707 squared. So if we multiply that out, we have our calculator here. So if we calculate this, 0.707 squared, 0.707 times 0.707, you see it's about 0.5, which makes sense. So basically we have 1 minus 2 times 0.5 plus 0.5. This is going to be 1. So it's 1 minus 2 basically, and we get negative 1. So if we compare it, this is exactly what we get. I'll use red here to circle it. So this is exactly what we get, about negative 1, which matches up with this result. So you go through the same exercise and plug in each one, and you'll find out you'll get this rotation matrix. So the best way to really interpret and go between quaternions and rotation matrix is to actually calculate it and see it. Otherwise, unless you have a super brain, if you just look at a number like this, it's actually pretty hard to interpret. So just plug it in and you can verify the results for yourself. So previously we talked about quaternions. In this video, we're going to talk about the transformation matrix and the two interpretations. We'll talk about how to multiply them, find the inverse, and deal with translation and rotation only. All my code and doc and some advanced examples will be in the link in the video description. So the transformation matrix takes one frame, frame 1, to frame 2, described by some distance. We're using a vector p, p1, p2, p3. So the idea of the transformation matrix is we want to describe one frame, the position and orientation relative to another frame. So we talk about the vector p, and the rotation comes from the rotation matrix, which we talked about previously, which we learned is that the 3 columns here represents the 3 axes that we're describing frame 2 relative to frame 1, which we saw in some of our previous videos. So when you take the 2 components and put them together, then you have your transformation matrix. One thing to notice is that there's going to be a padding at the bottom here with 3 zeros and then a 1. This makes sense because when you do some of the multiplication in vector form, it actually ends up looking cleaner when you multiply it out. So this right here is an example if you want to have a vector, and let's say you have one vector described in frame 1, we call v1 here, and then you might have another vector v2 described in a second frame. So in these cases, you can also use a transformation matrix to help you describe a different vector in a different frame. So to do that, we have our transformation that brings us from frame 1 to frame 2. You multiply it by v1, and then we'll get v2. So to look at this, we have the v1 with that little tilde on top. This is basically v1 padded with a 1 on the bottom to make this a 4x1 vector. And when you multiply it out, you end up getting r12 times v1 plus p12. So what this says is basically you have a vector, you rotate it, and then you translate it. So that gives you the vector that we see here, v2. So it's basically a series of rotation and translations, which is all captured within the transformation matrix when you see it in matrix form. Now, when we're talking about transformation matrices multiplication, you need to pay attention to which frame is going between. So when you have a transformation that goes from 0 to 1 and then 1 to 2, we could actually get the transformation from 0 to 2 by multiplying the 2 transformation matrices. So t01 times t12, you get t02. So more generically, we could say t0n is going to be t01 times t12 times t23 all the way to tn minus 1 times n. So this is the most general form of transformation matrices, and this allows you to essentially hop between frames by multiplying it out. One thing you want to make sure is that the inner values here for the frame should match. That way you know that they're physically connected to each other. So when you want to find the inverse of a transformation matrix, what this tells us, you can actually find the transpose of your rotation matrix, because when we talk about the rotation matrix previously in some of our older videos, we know that the transpose is the inverse, and that allows you to go between, say, 0 to 1 or 1 to 2. Transpose is the same thing as inverse. And then with the vector, you would have the negative rotation transpose times the original vector p. So this will bring us back from frame 0 to frame 1 or 1 to 0 if you use the inverse. So here's a visual that shows you could go back and forth. T01 goes from 0 to frame 1. T10 goes from frame 1 to 0. And if you want a translation-only transformation matrix, the rotation component is going to be the identity matrix, and then the vector here is going to be your px, py, pz. And if you want a rotation-only transformation matrix, then you would have the vector part 0. Here is actually a 3x1 vector of zeros. And then you have your rotation matrix only. So that's how you could have a transformation or translation only and rotation only matrix. So here we are again with our UR robot, but this time we're going to find the transformation matrix of our tool end relative to the base. So we have a script here called transformation matrix.py. And you can see right here, what we have is we're pulling our translation by getting the translation component. We're getting the rotation from the rotation component. And then we transform the quaternion into a rotation matrix, and then we concatenate our matrix into our 4x4 matrix, and then we print it out. I went ahead and built it. And if I run the ROS to run your kinematics transformation matrix, we see the output of our transform. So I'm going to go ahead and screenshot this and put it on Paint for reference. So I'm going to open up a Paint window. We have our transformation matrix, and this is our robot here. And let's take a look at what this actually means. So if we take a look here, let's use my pen here, and we could read it off. So the general structure, you can see right here, it follows the same structure as any transformation matrix. We have zeros here followed by a 1, which is the general structure. And we could review again the rotation matrix as before. So this tells us that the first axis is going to be, we see a -1 here. So it means that the x is in the negative x, which agrees. So this is the x, and this is in the negative x direction, so opposite direction, which makes sense. And then this other component, we see a -1 here. So this -1 means that the y-axis is in the -z direction, which agrees because right here is a z. And then this part right here, we have the other part of the axis. So we see is in the -1 direction. So this means that it's in the -y, because right here is the y, and then this one is in the -y direction for the z-axis of the tool end. So this is the rotation part, which we've talked about before, but the new part that we've added now is the translation. So this corresponds to the x, y, z translation. So if I were to draw a vector here from the base to the tool end, this is what this value expresses. So you can see in the x direction, the magnitude is to the -4. In the y direction is to the -1. So basically from here, you can see there's a small offset here. This is the y offset, which is this value here in the negative direction, which makes sense because y is pointing this way and the offset is going this way. And then in the z direction, this is our biggest value of 1.079. So that offset is basically this that you measure here. That is my z offset from this value right here. So all of that makes sense in terms of the magnitude and direction. So this is basically our transformation matrix. All right, in this video, we're going to talk about DH parameters, the difference between modified and standard, frame assignment procedure, the different types of parameters, the DH parameter transformation, and I'll go through an example. You can follow along with my docs and some more advanced examples, link in the video description. Okay, so DH parameters. DH stands for Dennevit-Hartenberg. So these parameters are used to determine the frame locations on a serial link robot. So a serial link robot is something that has joints like this that's connected between with links. So it has to be in this configuration where it's one joint, one link, one joint, one link. When there's several joints, for example, like this, that go to some base, these types are called parallel type of manipulators, and the DH parameters don't typically apply for something like this. So the key requirement is that it's going to be a serial link robot. So let's take a look at the difference between standard and modified DH parameters. So you want to make sure you're choosing the right convention. So on the first column here is going to be standard. The second one is going to be the modified. And some of the main difference is the frame I attachment. So for the standard, it's going to be I+1. Modified is at joint I. The transformation order is also going to be a little bit different. We have the link parameters index. So on the distal frame is I. For the modified, it's going to be I-1 here, you can see. And then it's common in these textbooks like Spong's textbook, MATLAB Robotics Toolbox. For the modified, it's going to be in the most popular textbook, Craig's textbook. That's the one that I went through most of it through college. That's a pretty common one. And then the parameter tables, you're going to see it's going to be basically the same structure, but it's just the way it's referenced is different. So we could see the frame assignment procedure. This is going to be the procedure that we will follow. So this is going to be for the modified DH parameters. All of this will make more sense when we go through an example, but I'll just quickly walk through the steps. So first you want to place the origin. We're going to be using the common perpendicular, and then we want to define the ZI axis, which is going to be along the joint axis I. We have the XI axis. This is going to typically be the common perpendicular. And if the axes intersect, it's going to be normal to the plane they form. And then the y-I axis by the right-hand rule. So if you have like x here, right, and then z here, then we know that x curl to y, z is up. So by right-hand rule, we have y is going this way. So just use the right-hand rule to get the last axes. And then another thing that they typically do to simplify some of the math is you want to make sure the 0 frame, base frame, matches the first frame at the initial configuration. And you typically want to choose the n so that you have as many zeros as possible so that the math is as simple as possible. So there's 4 main parameters. We have right here, link length. We have the A parameter. We have link twist, alpha, link offset, di, and then the joint angle theta. So the subscripts here just tell us, the different relative frames that we're looking at. That's kind of how they defined it. So it's defined as the first one is the distance from the z-axis along the x. The next one is the angle between the z-axis about the x-axis. The link offset is going to be the distance between the x-axis along the z-axis, and then the joint angle is going to be the angle from the two x-axis about the z. So DH transformation matrix, this is going to be computed for each one that we had. We're going to create a transformation matrix. So when we create a table with all the parameters, we're essentially going to do a series of rotation, translation, rotation, and translation with the parameters that we found. So if you go through the process and plug it into the different matrices and multiply it out, this right here is the final result that we get. So this is the transformation matrix that will describe your transformation from one frame, if we call this like frame 0, to the next frame, which we might call frame 1. So this is going to be the transformation matrix that's going to define the transform between each joint on a serial robot. And note here we have some shorthand. Cx is going to be cosine, Sx is going to be sine. So it's just a shorthand to write the sine and cosines to make it look more compact. So a lot of the theory can be applied in practice if you start doing projects. So I'll leave some link in the video description where you could get some of the fundamentals of robotics and AI and some projects that you can get started with. All right, now for an example. So this is a 2RR, meaning there's 2 revolute joints. We have our first one right here, and this is our second one. So it's a 2RR robot. Right here is in a 3D view. So you can see we have defined our frame 1 for joint 1, frame 2 for joint 2. And then these blue here is our axes that we're going to be referencing later on. So this is a 2D view now, so making a 2D to kind of see the axes a little bit better. So we see that we define our x-axis here pointing to the next z-axis, and there's this second x-axis pointing to the tool end. And then the y-axis here, you can see we just defined it using the right-hand rule. So this is our frame assignment using the procedure. And you can see from here, we want to define our 0 frame. So this right here is our 0 frame. We just made it basically orthogonal to the page just to keep it simpler. And then theta 1 is going to be some rotation once there's an angle theta. So we also added a tool end here. You can see this right here. This is our frame 3. And what we did is to keep it simple and make sure the x-axis is pointed in the same direction. So that kind of simplifies some of the math later on. And this right here, you can see this is our next one. This is where we're going to define some of the parameters. So we have our theta 1 here, theta 2 here. This will describe the joint rotation of each of the joints. And we also define some new lengths here, L1 and L2. So this is going to use all of these parameters later on to define our DH parameters. So if we fill out the table, this is what it's going to look like. You can see that we have 1, 2, 3. This 3 is going to be the tool end. So notice that this one is just angle 0 for theta. The active joints here are theta 1 and theta 2 because they contribute to the actual joint motion. So these we will leave in variables. And then we have right here, these are the offsets between the different joints 2 and the tool end. Now, if we take our equation from the transformation matrix from previously and take all the parameters and plug it in, we will get our 3 transformation matrix, T01, T12, and T23. So all of these transformation matrix will describe the transformation between the different frames. And the most important part is we could use this result to do some of the 4 kinematics later on. Okay, so I have a script here that's going to help me figure out the DH parameters from my UR robot that we see here in RViz. So let's take a look at that script first. So this right here is called the DH parameters. You can see right here we have a class here called DH parameters node that will pull in our kinematics from our default kinematics.yaml file. We have a RPY to matrix conversion. We have a DH from URDF origin. This is going to get some of the parameters here. And then this is the main function here that prints our DH parameters. And you can see we're using the modified DH parameters. So basically we're going to run this script, which I ran here, and we could verify some of the output. So just for reference, I'm going to just screenshot this and we'll put it in Paint so you can see it side by side. So these are the parameters, and I'll go through one at a time. I already wrote it out, but let's just go through one at a time here. So this first one here is joint 1. Okay, so joint 1 is from base to shoulder link. So if we look here, we have our base to shoulder link. So if let me just get a copy of this. So we have our base to shoulder link, and if we want to verify this, let me get the right pen color. So the D parameter here, so we're looking at the first line, right? So all the parameters are 0 except the D parameter. So this D parameter is the height along the Z axis. So if we try to measure this height here in the Z direction, basically this one is our 0.1625. And the rest are zeros because it makes sense because we just have a Z offset. So that's why we have all the other ones are 0. Now, if we come back here, our next one, I'll just copy this over. This one is going to be our joint 2. Okay, so joint 2, what we have here is it's going to be shoulder link to upper arm link. So if I come here, we have our shoulder link to upper arm link. Okay, so if we look at this, you can see the upper arm link is basically rotated. Okay, we see a rotation. I'll put this down here now. So we see a rotation to here. Now, if I use my brush tool, you can see a little bit better. Okay, so we have a rotation that went this way, and this is a rotation. Actually, really quick, before I continue, I want to first actually make sure that all the joints are at 0, 0, 0. So we started this from previous, but I'm going to run the joint trajectory here. I'm going to first start up my joint trajectory controller here. So this is going to start the controller. And then what we want to do is just send it zeros. So I'll copy this and then I'll paste it here. I want to modify this the second joint here to be 0. And the reason we're doing this is because, if we're looking at the DH parameters, all the joints should be 0 to be looking at the true frame. So you can see it does indeed move. So this is the true 0 position. So that's why we're moving it. Okay, so we noticed the first joint that we looked at didn't change too much. But if we now look at this joint, the second joint, now this one has moved, right? So this upper link here is now the green is pointing upward. And if I screenshot this, we could go back to here to look at it. Just going to delete this because it's getting a little bit crowded. Okay, so this is our joint here, and we notice that it's hard to see because it's the same color, right? But you can see the original z-axis is pointing up, and then now y is pointing up. Actually, a better way to look at this is if I suppress a shoulder link. Okay, so this is a shoulder link. Initially, the z-axis is pointing up, and now the upper link, the z-axis, is pointing this way. Okay, so that's a better way to look at it. So what we're saying here is that initially we have z is going this way, and then now z is going this way. So this is a 90-degree rotation about the x-axis. So this is what this alpha is, which is alpha of pi 2. And the rest of the parameters are 0, which adds up to our expectation. Okay, so now let's take a look at the other joints. I'll delete this now so we have some space. Okay, so if I come back here, let's look at our joint 3. So our joint 3 here, this is the one we're looking at. So it's going to be upper arm link to forearm link. Okay, so we have our upper arm link. I'll suppress this to forearm link. Now, if we look at this transformation, again, I'm going to screenshot this over here so we can see it. Okay, so we have now, if we look at this, we're looking at the third one now. We have 0 parameters in most of these, and the only thing we have here is the a parameter. So this negative 0.425 is basically the distance along the x-axis in the negative direction, because this way is positive x. So the distance here is 0.425 in the negative direction. So that confirms the a parameter here. Now for the next one, this is going to be a forearm link to wrist 1 link. Okay, so this one right here, I'll go ahead and delete it again to make room. I accidentally drew too much, and I'll delete this again. Okay, so this one right here now, we're looking at forearm link to wrist link. Okay, so I'll suppress this one, and then I'll show you the wrist one. Okay, so let's go ahead and screenshot this. Okay. Now for this one, we actually have 2 parameters. Okay, so this is the one we're dealing with now. And let's take a look at the first one. So the forearm length 392. This is in millimeters or meters, 0.3922, right? So this is basically this distance here. And again, it's in the negative x direction. So that gives us the 0.3922. And then the d parameter, this is the offset along the z-axis. So it's this shift that we see here. If I draw it out like this, this is the offset here. This is going to be 0.133. And it's positive because this is our positive z direction. And then because the z-axis are parallel, we have an alpha of 0. Okay, so that one makes sense too. Now we'll move on to the next one. The next one here is wrist 1 to wrist 2. Okay, so come back here to my paint. All right, wrist 1 to wrist 2. So I'm going to go ahead and comment out. Actually, yeah, just comment out that one. We'll keep wrist 1. Now we have wrist 2. So we see here it's simply offset down with some rotation as well, mostly to align the z-axis now. But what we see here is the d offset. So d is going to be the offset of point. Let me change my brush here. So we have the z offsets, right? And that's going to be this distance here that we see here, which is 0.0997. A is going to be 0, and then alpha, we could see the axes got rotated. So the green was initially up, or we could look at the blue one. Z was initially this way, and Z is now down. So it's a rotation of 90 degrees. So that confirms our visual inspection of the frames. Now, finally, for the last one, I'm going to come back here to my README. This is our joint 6. go ahead and paste this here for reference. Now, if we come back to here, I'm going to suppress this one, and we have our link 3. We see there's the offset. Okay, so this one right here, again, it's offsetting this way. Change my brush tool here. So this distance, 0.0996. And then now we have a rotation. You can see initially it was pointing down, now it's pointing this way. It's a rotation in the negative x direction, so that gives us negative pi halves. So this confirms all of our DH parameters for the UR robot. So hopefully you got a better understanding on how to do that. So previously we talked about DH parameters, and that sets us up to start talking about forward kinematics. We'll go through an example so you could better understand how it works. You can follow along with my code and documentation and some more advanced examples in ROS, link in the video description. So imagine you're given the angles of each joint of your robot. The goal of forward kinematics is to find the position and orientation of the robot's tool end. So this is a problem of forward kinematics. Basically, angles in, final transformation out. So based on what we described, you could write your forward kinematics in this expression where it's a function of the angles, where we're calling the angles q, which could be a vector of thetas 1 to up to theta n. N is going to be the total number of joints in your robot. And T0n is a transformation matrix that takes you from your 0 frame to your n frame. So the n frame could be like the tool end of your robot, for example. This could be your n frame, and then the base frame could be 0. So what you have for this when you expand it out is going to be the multiplication of all your transformation matrices from the base to the tool end. So you see right here, we have 0 to 1, 1 to 2, and so on. And you could also write it in a more compact form right here. We're just suppressing some of the parentheses and input arguments for the theta, and just write it simply as T01, T12, and so on. So when you multiply it out, you could write it in symbolic form where the middle part, this is a 3x3 rotation matrices, and then you have right here, this is going to be your position vector that describes your base frame to your tool frame. So in this transformation, you're getting the orientation and position information. So previously where I talked about each of the intermediate transforms, that part is derived from the DH parameters, which we talked about previously. And then you just basically multiply out all the transforms and you have your forward kinematics. Now, before I get into an example, if you want to get started in robotics and AI or build your portfolio with robotics projects, make sure to check out the links in my video description. All right, so here we have a 2 degree of freedom robot as an example. So right here we have our 2 frames here, the frame 0, which is our base frame. 1 is going to be for joint 1. We're using theta 1 to describe the angle between the 2 frames. We have frame 2 here for the second joint, and we're using theta 2. And lastly, our tool end here, this is going to be frame 3. So to describe the tool end, we use the transformation matrix T0n. And then we also have some links here that describe the distance between the frames. So now that we have everything defined, we could find our intermediate transformation matrices. So we have T01, T12, and T23. So all of this is derived using the DH parameters, which we talked about, and we just plug in the parameters to get these transformation matrices. Now, to get the final transform, which describes the forward kinematics, what we do is just multiply out the 3 transformation matrices, and we get our transform, which we call T03. And this is the final result here, which is basically going to describe our tool end. So we have some simplification here where C1 is going to be cosine, S1 is sine, C12 is going to be the product of cosine, and then we have sine, which is going to be the product right here. So all of this is going to give us our forward kinematics, which can tell us the tool end position and orientation. So we'll go through some cases to see if it actually makes sense. You can see in this configuration right here, we have our angles all at 0 degrees, which is the arm fully extended. So when it's fully extended, let's see if the rotation matrix makes sense. So this is the identity. So it means that they're pointing in the same direction, which indeed we see the x's are in the same and the y is in the same. So yes, it's pointing in the same direction. And the position vector here is going to be only the x components. We have L1 plus L2, L1 plus L2. So this is the total length that goes from the 0 to frame 3. So it actually makes sense. This configuration is what we expect looking at it visually based off of the results. And here is yet another configuration. So you can see this one right here is in 90 degrees. So we want to find the tool end. So if we take a look right here, you can see that at theta 0 and theta 2 is 90. We could plug it in and let's take a look at the interpretation. So this part is the rotation matrix. So 0, 1, 0, what does that mean again? It means that the x-axis is pointing in the y direction. So x-axis right here, yes, is pointing in the y direction. Now the y-axis here, negative 1, 0, 0, this means that the y-axis is pointing in the negative x direction. So y-axis, x direction, this is positive, so it's in the negative direction. And lastly, the z-axis, 0, 0, 1, meaning it's in the same direction. So z is out of the page, z is out of the page. So that makes sense. And then for the position vector right here, L1 and L2, it says that the x position is in L1. So indeed, you could see this right here, the distance in the x is L1, and the y direction is indeed L2. So we're going to take a look at the UR robot and figure out what the forward kinematics is. And it turns out that the forward kinematics was basically the transformation matrix node that we developed. So we're going to just look at a few cases of that and you'll see it in action. So I'm going to run this. I've already built it, but this will print out my forward kinematics. So you can see here, this is my transform. Again, I'm going to copy this and we'll take a look at it in Paint here. So I'm just clear this real quick. And if we look at this robot, I'll rotate a little bit so you can see the tool frame here. But yes, this is basically the orientation. So as for kinematics, what it's supposed to tell us is basically this vector, right? We have our base frame to our tool end. And what exactly is the distance, the vector that describes it, which we see here. And we also have the rotation matrix that describes a frame. So again, let's go through that exercise again. It's going to be very similar to what we talked about before, but just for completion, let's take a look at it. So if we have this, what we have is the first axis, right? We have 1, 0, 0. This means that the x of the tool frame is pointing in the x of the base frame, which matches our visual inspection. 0, 0, 1 here means that the y-axis, this one, is pointing in the z, which matches our expectation. And lastly, we have 0, negative 1, 0. So this means that our z-axis is pointing in the negative y, so opposite of the y direction of the base frame. And again, that matches our expectation. And then here we have our x, y, and z component. So in the x direction, from here to here, this is going to be our distance of 0.8172. This is in the negative direction because this way is positive x. And then in the y direction, we have an offset of 0.2329. So this is going to be this distance here. If I measure this, this is going to be 0.2329. And then lastly, we have our z offset. So if I draw it out like this and some distance here, basically this is our z offset. This is going to be 0.062. So it's just a tiny offset slightly above the base, and that fully defines our forward kinematics. And the idea is, our forward kinematics can take in any angle and will output our transformation matrix. Right now, our current angles are at all zeros. But you could repeat this process by updating the angle, say, from theta 1 to theta 2, like, for example, at time 1 or time 2. You could have a different vector for the thetas, and then you'll have a new transform that describes the new tool end. So that concludes the summary for kinematics for our robot. And in this specific one, we were just using the URDF frames that they got from ROS. So previously, we talked about four kinematics. In this video, we're going to talk about inverse kinematics, specifically the analytical solution. We'll go over a 2DOF robot example and a UR robot example in ROS. If you like the code and doc to follow along, make sure to check out the link in the video description. So the inverse kinematics problem states that given the position and orientation of the robot, you want to find the angles of each joint. So typically the input to the inverse kinematics could be a transformation 4x4 from the base to the tool end, and the output would be all the angles theta 1, theta 2 up to theta n. So let's take a look at an example. So this one is a 2R robot that we've been working with throughout the series, and let's say we already found the four kinematics as described by this 4x4 matrix. If you want to see how I derived it, I went over in the previous videos. So you have here the equations for your four kinematics. Let's start off with just the position. So we have the x, d, and yd, d meaning desired. So it's your desired x and y position. The z component is 0 because it's a planar robot, so we're not going to worry about that. We have our cosines right here and sines here, which we're expanding out. So this is just the expanded form. Once we have that, we could start doing some algebra. So using the cosine plus sine property equals 1, and the cosine A, cosine B plus sine A and sine B, this gives us the cosine A minus B. So using these properties, we could say that cosine D squared plus YD squared equals this right here. And the main thing we're solving for is going to be cosine of theta 2. Once we do that, then we could solve for theta 2. We're going to get an arc cosine of this expression right here. So this is how you get theta 2. Now we have to find theta 1. To find theta 1, we go back to our equations here. So we expand the four kinematic equations using the angle addition identity here. We have the cosine theta plus theta 2 equals this expression. So once we have that, we have our xd and yd, and notice we have our cosine and sine terms here, sine and cosine. So what we can do is do some little tricks. We have k1 equals L1 plus L2 cosine theta 2, and then k2 equals L2 sine of theta 2. So since we already know theta 2, we could plug it in. So we have xd as a function of these k1 and k2 here. And then same thing with yd, we have those expression. So these are our different expressions. And if we go to the next page, you could see we just do more manipulation with the different variables. Then we could replace the variables, and we have xd equals r cosine of theta 1 plus gamma, and yd is r sine of theta 1 plus gamma. We take a tan 2 of both, and then we get this expression. So we have theta 1 plus gamma. Then all you need to do is substitute it back in. Then we solve for theta 1. We get a tan 2 yd xd minus a tan 2 of this big expression. If I slide over, you can see this is the remaining of the expression that you have to plug in. So basically the idea is we have everything we need, right? Because we solve for theta 2. Now our last variable is theta 1. So we have the equations for theta 1 and theta 2 given our tool end position xd and yd. Now, before I jump into the example for the UR robot, if you're looking to build your career in robotics and AI, I have a bundle on my website, as well as a lot of robotics projects to help you get started. Link in the video description. Okay, so here we are in ROS. I'm using WSL here. You could use this either natively in Ubuntu or WSL on Windows. So right here, I have an inverse kinematics node that I'm running, and I'm also doing a couple different things. So you'll get all of these code when you get my robotics bundle package with my code and documentation. You could run these examples for yourself. But let me just show you exactly how it works. So this one right here is going to be relying on an analytical solution for this UR5E robot here. You can see in the back, my big head is kind of blocking it, but you can see this is our UR robot. So the idea is we want to be able to find the joint angles given the tool end position. So I have a couple of different scripts right here. So right now, you could start it up. You could start up the robot, and then you could tell it to move. So if I come here, you could see if I run this command here, the action send goal. So if I send this, right now it's going to move to this new position here. So this is the position of the robot we're dealing with. And what we can do is figure out the transformation matrix of the tool end. So if I run this, you can see this is the tool end of my robot here. So now that I have the robot in a new position, I know the tool end. So the idea is we want to figure out the exact angles for this. So you could run this right here, ROS2 echo topic. This is using the ROS way to show you the topics. So notice the order of these is a little bit off, meaning that the order is not exactly the same order as I sent it. But you can see that the shoulder lift joint is 0, the elbow joint is negative 1.5, and the shoulder pan joint is also negative 1.57. So these are in fact the same angles I sent. It's just the order in which ROS prints it out is a little bit different. But if I run the inverse kinematics, basically I am going to expect these angles from the output if the solution is correct. So that's kind of some way you could do some sanity check to make sure your solution is right. So I have the script here that can check the inverse kinematics. I wrote the inverse kinematics solution, the analytical form here. So what this does is you could pass in the transformation matrix here of the tool end, and we confirm that using this printout right here. This is the same matrix, as you can see. It's just going to be expressed in a slightly different form so that it could work in the ROS argument. So I'm just going to go ahead and copy that and run it, and you can see the output. And indeed, we get negative 1.57, 0, negative 1.57, and then 0, 0, 0. So looking at the output, it confirms that our inverse kinematic solution matches. So if you want to play with this program, you could check it out in the link in the video description. So in the last video, we went over the inverse kinematics analytical solution. In this video, we're going to talk about the Jacobian matrix and explain what it is and the physical interpretation, specifically the geometric and analytical version of the Jacobian. For the numerical one, it's going to be in a separate video. So we're going to be covering it with an example of the 2 degree of freedom robot, and then end it with a UR robot, which has 6 degrees of freedom. For the code and documentation, you can follow along, link in the video description. Okay, so what is the Jacobian matrix? And again, we're going to be talking about the geometric and analytical version. So what the Jacobian matrix does is it's going to map the joint velocities of your robot to the linear and angular velocities of the tool end. So mathematically, you're going to see it as this expression. So x dot, this right here refers to the linear part, as well as the angular part of the tool end of your robot. And then this q dot is going to be the vector of joint velocities. So you can see right here, q1 dot, q2 dot, all the way up to qn dot, right? So assuming you have n, this n here is the number of degrees of freedom, so DOF. And in this case, we could have a 2 degree of freedom or 6 degree of freedom. Now, the Jacobian in its most general form is going to be a 6 by n matrix. Okay, so you could typically break it down into 2 parts. So the top part I like to call JV, and bottom part is J omega. So one maps the linear part, and then the other part maps the angular part. So that's typically how you want to think about it. And you could see in here, this is the breakdown. So the top part, you could see it as the partial derivatives of P. P is going to be the vector that describes the base to the tool end. And you can see it's a partial derivative of vectors. So partial P divided by partial Q. This is going to be Q1 for the first joint, all the way up to Qn for the last joint. And then this right here, the J omega 1 up to omega n, is the angular velocity of each of the joints. So basically it describes the direction of the joint rotation, whether it's in the x, y, or z axis. And you can see right here, we've defined P. This is a vector, and it has the x, y, and z component. Sometimes you might see it simplified as just x, y, z, depending on where you're reading it. So there's usually going to be 2 types of joints for your robot. You have what's called the revolute joint, which is something that rotates about its axis. And you have a prismatic joint, which is a joint that moves linearly along its axis. So for the revolute joint, the expression to calculate the Jacobian, the geometric one, is going to be the z-axis. and the cross product of the vector between PE and PI. So PI, the interpretation of that is going to be the physical location of joint I, which is also going to be the translation column of T0 to I. Okay, so if you have your 4x4 matrix, it's basically going to be this part of it that describes the translation part. And then PE is going to be the n effector position, or the translation of the T0 to n. So it's going to be basically the final transformation that you would get from your forward kinematics. And ZI is going to be the axis direction of your joint. Typically, it's going to be the third column. So if you have your 3x3 matrix here, it's going to be the third column. And this is what we call our ZI, okay? And the prismatic joint is going to be very simple. You just have the ZI component and then 0 here. This is going to be a 3x1 vector of zeros. Now, this right here is a Jacobian matrix in its most general analytical form. So previously, I would count that more as a geometric derivation. For the most analytical one, you have a generic function here, which we call f. Okay, so this f is going to be the mapping that goes from Rn to Rm, which is going to be the forward kinematics expression that you choose. So you could have many different ways to represent it. So for example, you could have XYZ, and then you have your phi, theta, and psi. So you could be using different ways to represent your orientation. So typically the linear part, XYZ, is pretty straightforward, but you could have XYZ plus Quaternion, you could have XYZ plus Euler, and so on, because there's many, many ways to represent the orientation aspect. And to get the analytical form, basically, you would need to have your forward kinematics equation that describes it. Then you just take your partial differentiation of whatever form you have. Then that you would have your analytical Jacobian. Okay, so enough theory. Let's take a look at an example. So this is the 2R robot that we've been looking at, right? We have, again, a base coordinate of 0, 1. We have the second joint and the tool end. So if we take a look at our transformations, which we derived previously, we're going to be using some of these results to calculate our Jacobian. Now for our first column, the last column we call P1, and then we have P2 for our second transform, and then our third transform, we're going to be taking PE and P3. So for column 1, we apply J1 with the formula, and we find the difference between the position vectors, which our final result is this. And then we take the cross product. So when we take the cross product, we see that this is our final solution for J1. And then if we go on to the next column, we do the same thing. We have J2, plug it into this equation, find the difference of the position vectors. And then again, we do the cross product, which we will get this as our final solution. And then if we do it to the final part, we combine everything. So you can see we have Vx, Vy, and omega z, right? So if we take a look at some of the physical interpretation, you could see that this right here is our omegas. And because it's a planar robot, right, we have 2 degrees of freedom. It's going to see, we see that the joints are all in the z-axis, which makes sense. Now we can also write it in a more general form, which is right here, a 6x2 matrix. So obviously these parts are not contributing to anything. That's why we see the zeros there. And when you multiply it out, you'll see that some of these components will not do anything, which is basically these 3 is useless right here, right? So it's just fillers if you wanted to see the most general form. So now let's take a look at our UR robot. So this is our initial configuration that we're going to be working with. And we could run our script here, which will give us our Jacobian matrix. So the command we'll be running is ROS to run UR kinematics Jacobian. And if I run this, it's going to output the Jacobian. So this is our Jacobian matrix. And let's take a look at the interpretation of these values. Okay, so I put the matrix here, and let's take a look at the bottom portion, which is going to be the easiest ones to interpret. So this again corresponds to the angular velocity. And if we take a look at where the ones are, you can see that this one has the 1 at the bottom, and then also this one. So this tells me that J1, this is 2, 3, 4, and J5, tells me that J1 and J5 are the ones that contribute to angular velocity in the z direction. So the z direction is pointing up, and you can see J1 is pointing up, and then the next one is J5, which is this joint. So that agrees with my visual confirmation of the two joints where they're pointing. And all the other joints, you can see this one is in the y, this is another one in the y, y, and y. So all the other four axes are in the y direction, which is this green axis. So you can see this is J6, this is 4, 3, and then joint 2. So that agrees with our visual confirmation. So now for the top Jacobian, so this is going to be representing the linear velocity. So the linear velocity, you can see actually most of the motion, if you compare the magnitude of the values, most of it is going to be in the x direction. So what this tells you is that if any of the joints try to move, most of the velocity that's going to be generated is going to be in the x direction. So the x direction is the red axis on the bottom that you can see here, which is, pointing towards us. So that means that it's going to be causing a velocity in that direction no matter which joint is moving. But one thing to note is that the last joint, it's all zeros, right? So that means that this joint right here, if it's spinning, no matter how it's spinning, the tool end is not going to be moving at all. So that agrees visually based on what we see, because the last joint rotation does not move linearly the position of the tool end at all, just the rotation. So it makes sense that the last column is all zeros. Now, if we take a look at the magnitude of these values, right, we see that this is 0.9 and this is 0.4. This makes sense because if you compare joint 2 and joint 3, right? Joint 2 is at the base of the robot, closer to the base. Joint 3 is at the elbow. So the amount of motion coming from J2 is going to cause a lot more change in velocity for the tool end as opposed to, a joint that's closer to the tool end, which is like joint 3. So the magnitude makes sense. And the negatives, it just means that the direction of the rotation is opposite of the base y-axis. Okay, so in my last video, I talked about the Jacobian matrix, specifically the analytical and geometric version. But in this video, we're focusing on the numerical version of the Jacobian matrix. So we're going to cover two examples, one with the 2R robot and then another one using the UR robot. You can follow along with my code and doc, link in the video description. Also, for any behind-the-scenes videos, make sure to check out my Robotics Builders membership. Okay, so as we talked about last time, we have our Jacobian matrix here, which we call J, and this is going to be your partial derivatives with respect to your joint angles. So we have partial F1 over partial Q1, and for the first row, it's going to be the same F1, but we change the Q's from Q1 all the way up to Qn. And then down the columns, we maintain the Q1, and we're just changing to F2 all the way up to Fm. So we have F right here. This is going to be our four kinematics definition. So we have our different components, F1, F2, all the way up to Fm. And the way you define the F is going to be up to you. So there's a couple different options. So the part that's going to stay the same is the linear part. So X, Y, Z will stay the same. But the rotation part, you have a couple options. You could do Euler Angles, Quaternions, or rotation matrix, just as a few examples. So if you choose Euler Angles, notice this is the linear part. The linear part is going to be the same for all three of these, is the X, Y, Z. If you have Euler angles, you might have three sets of angles here. For Quaternion, you have 4 Qs. And then for rotation matrix, you could just grab the components of the rotation matrix, linearize it from R11 all the way up to R33. Now, to approximate your Jacobian, you could have different ways of doing it. We have the forward finite difference, we have the backward, and the central. So Now for the forward difference, you see our forward kinematics is going to be being subtracted here, and you're going to take a term from your forward kinematics and take the current set of angles and perturb it in a direction which we call E right here, and you divide it by that small difference. For the backward, we basically flip it. So now we have our forward kinematics computation first, and we subtract it from our forward kinematics, which we're doing a minus a small difference. And then the central finite difference is basically taking the forward and backward parts. So this part we saw it in the forward, this part we saw in the backward, and basically subtract the two, and then we divide it by 2 epsilon. So this is basically a combination of the two. Now, as an example, we could take our Jacobian matrix, and we have here, this is going to be each one of our vectors. So we could plug in the vectors, so f1, f2, and fi, where q right here is going to be your vector of joint angles. And then you could plug it in for each row. Now this ej hat term, this is like a selector. So it's going to choose the jth position to choose the right angle. So it'll point to the right direction that we're trying to add the epsilon. And then the q plus epsilon e hat, this is going to ultimately come down to selecting that specific joint angle and adding some small epsilon to calculate our Jacobian. So this epsilon is going to be something that you define. So typically something small like 10 to the negative 6 radian. You could play around with this value to see what works best for you. Now you can see our example that we've been working with, which is our 2R robots. You can see this right here is our forward kinematics, which we grab F1 and F2. So these are pretty much our X and Y position vectors that describe our position of our tool end. So if we take our column 1, so the idea is to perturb theta 1 by adding some small epsilon to our value. So we have our partial f over partial q. We take our equation and we plug it in for our forward kinematics. You can see this is our final equation. And same thing for column 2, we're going to perturb theta 2, so q plus epsilon e hat 2. So you're adding some amount to theta 2 now. And again, you plug it in, and this is going to be our final equation. Now you can see we could take our 2 previous results of our 2 columns, put it in matrix form, and this finally we have our numerical Jacobian matrix. So now let's go over an example with our UR robot in ROS. So we have our code here. We could just run ROS to run UR Kinematics Jacobian Numerical, and this is going to get our numerical Jacobian. And you can see this is our output, and we could compare it with our previous results, which I covered in my last video. So in my previous video, I described a lot of detail in terms of what each column means. So you could just refer to that video for the physical interpretation, but at least we see that the results match between the numerical and geometric. So previously we talked about inverse kinematics using the analytical approach, and we also talked about how to generate the Jacobian matrix using the analytical and numerical approach. So this really sets up our foundation to understand the numerical inverse kinematic solution. So this is going to be the most general way to figure out the inverse kinematics for almost any robot. And we will cover an example using the UR robot. If you'd like to follow along with my code and documentation, check out the link in the video description. And for some of my behind the scene videos, make sure to join my Robotics Builders membership. So just as a refresher of what inverse kinematics means is that you're given the position and orientation of your robot. So typically that's going to be a transformation matrix. And the goal of inverse kinematics is to find the angles of each joint, which we're calling theta 1 to up to theta n. And in short, we call inverse kinematics IK, which we have right here in this middle box. Now, to calculate the inverse kinematics using the numerical approach, the core idea of it is that we're relying on some error vector. So this error vector is the difference between here is your initial position, and we have some final position or target position that we're trying to reach. So it's really having this core concept of moving from one point to the other, but in practice, this movement between the 2 points is very, very, very small. So the general approach is to minimize this pose error that we talked about. So we could define this error using the equation here. The top part is going to correspond to your position error, and the bottom part is going to be your orientation error. So this epsilon d is the orientation error, and it really depends on your representation. So in our case, we're using the axis angle. So this is going to be the difference between your your desired rotation matrix, and the current rotation matrix. So when you write that out, it's going to be the cross products of the 3 vectors of your matrix, and this is going to give us our epsilon. Now, a core concept this uses is what's called the Newton's method. The idea of Newton's method is to find the zeros of the function. So you can imagine you start off with an initial point here we're calling x0 and y0. Now, given this point, we want to find the tangent vector, which is this line in green. This is a tangent vector to that point. So when you draw the tangent line to that point, we're going to obtain a new point, which we call x1 and y1. So the slope of this vector we could call m, and that's going to be y1 minus y0 divided by x1 minus x0. So we know that the slope is also the derivative, right? So we call this f prime of x of n. So if we plug in the values, right, we have at y1, this is going to be at the x-axis where we have y equals to 0. So this is where this 0 is from. And y0, we're calling it more generically f of x of n. So this is where this term comes from. And then the bottom is just more generally, we have x of n plus 1 minus x of n. So basically the 2x parts of the 2 points that we have here. Now, if we solve for x of n plus 1, we get the expression x of n minus f of x of n divided by the slope or the derivative. Now, the idea is to repeat the process. You could see we have our second line here that we drew. So you repeat the process until the point has an error that gets very, very close to 0. Basically, our goal is to find this point, which is the 0 of the polynomial, or where the polynomial intersects the x-axis. So that's our target goal solution. And the distance between these 2 points, this is the error that we're allowing. So whatever that defined in your algorithm is, that's going to be how many times your Newton method is going to iterate until it stops. So you're never going to have a perfect solution. There's always going to be some trailing values because numerically there's always some error. It could be as small as 0.000001, but there is still some error and the user will have to define that. Now, the error equation you can obtain from this expression here, where you have your desired forward kinematics minus your current forward kinematics. So usually this f desired here is going to be the controlled point that you're telling it to go to. And you can see right here, the derivative of your error is going to be f prime here. And we could have this equation here that will tell us our new joint position, which we have q of k plus 1. And that's going to equal our initial q, which we're calling q of k, minus the error of q of k divided by the epsilon or e prime of q of k. So if you solve everything, you're going to get this equation here, and this is our result. But if we want it in the most general matrix form, we're going to substitute that with the Jacobian here. And specifically, this Jacobian that we have is called the pseudo-inverse. So you could think of this right here. So 1 of f prime is going to be j to the negative 1. If it's a square matrix, it's fine, but most of the time you may not have things that's so pretty. So the most generic case is what we call the pseudo-inverse. And the pseudo-inverse, you could compute it using this expression here, j transpose times j of j transpose to the negative 1, or the inverse of that. Now, to summarize the algorithm step, this is basically your pseudocode. So you're going to have your initial guess, which we call Q0. You set some tolerance, epsilon, and a max number of times you want to loop it. You compute the forward kinematics. You calculate the error. You want to check the conversions. If it's converging, then you could exit the loop. You compute the Jacobian, and then you solve for your change in angles. Then from there, you update your new guess or your new set of joint angles. And then from there, you step your counter, and then you repeat until you reach the endpoint based on the tolerance that you've set. Now, you might see different variations of the solution. So there's one called the damped least squares. So this one is some additional terms that you modify to this part, where previously we've had our pseudo inverse, but this right here is the damped least squares version. So you're really adding this part here. And this is good if you want to avoid large velocities near singularity. So by adding this term, you're putting different weights essentially at different joints. And then another approach too is to use what's called the Jacobian transpose. So this is the solution for that. It's faster to compute in general, but it's going to be slower on conversions. Now let's take a look at our example here with our UR robot. We're going to figure out the inverse kinematics using the numerical solution. So we have a command here that says ROS to run your kinematics, inverse kinematics numerical, where we pass in the transformation matrix. So you could obtain the transformation matrix by running the transformation matrix function, which we went over in our previous video, but this will essentially give you your forward kinematics, and you want to pass in the forward kinematics as an argument to this function. So I've went ahead and got that transformation matrix, and then the command right here, if I hit enter, you can see this will compute our inverse kinematics. So the inverse kinematic solution, you can see right here, there's a slight numerical rounding error. That's why it's not perfectly, like right here, it's not perfectly at 90 degrees. That's some things you could tweak in your code to make it more precise. But you could see if we were to check the joint states, we could run this command ROS to topic echo. And this is essentially going to give us, I think I have my command here already. If I run this, you could see it's going to output the joint states. And you can see that it matches our expectations. Notice that the order of how they output it is slightly different. So the pan is last instead of first. So you just need to swap that to get the right order. But you can see basically it's like all zeros except the first and third, which in here is a second and fourth. So it matches our expectations, so we know that our inverse kinematic solution is correct. So previously, we talked about the inverse kinematic solution using the numerical approach. In this video, we're going to talk about the joint space trajectory. We'll see an example with the UR robot, how to generate smooth trajectories for each joint. You can follow along with my code and documentation, link in the video description. So let's say you have a robot in this starting configuration and you want to move it to a new configuration. This is where the joint space trajectory comes in. So we call these 2 points the initial joint angle, and we have a final joint angle. So you have the smooth trajectory that we're going to obtain for each of the joints. And this is what we call a cubic polynomial. So this is a third order polynomial, and we have these coefficients A0, A1, A2, and A3. So if we place special initial and final conditions, we could guarantee this trajectory to be smooth. So smooth means that the initial velocity is 0 and the final velocity is 0. So specifically, what does that mean to set up our equations? So you can see we have an equation that has 4 unknowns, and we could generate 4 equations from our initial conditions. So you can see right here, we have our initial position. This is where we start. And we have a final position. This is where we finish. And we could set the initial and final velocities to be q dot 0, and this is the q dot naught, and we have the q dot final. So these are our initial and final velocities, and typically we set these to be 0, so that also simplifies our equations. And you can see right here, if we solve for the constants, we get these equations. So the constants for the first two is going to be q0 and q0 dot. And then A2 and A3, you could solve it and you'll get these equations. So we have the equations for the 4 constants, and then you could solve for it. And if you want to do it by hand, you could see these are the different expressions for the polynomial. We have q, the first derivative q dot, and then q double dot. So once you have a system of equations, you could solve for the A0, A1, A2, and A3. Now you can see the top graph is our position graph. So if you were to take the derivative, then you would have the second graph here. What the second graph tells us is that the initial and final velocities are both 0, which agrees with our initial and final conditions. And if we take the derivative once more, which is our third graph, this is going to give us our acceleration. So you can see that at the very peak of our velocity, we have an acceleration of 0. So you initially start with a accel phase, and then you have a decel phase. Now, in some cases, you might want to place additional constraints to the acceleration. So we didn't do that previously, but if you did want to, then you would need to have more equations. And to get more equations, you need to have a higher order polynomial, such as the quintic polynomial. This one goes up to a 5th order, so that way you have more equations. If you were to solve for it, you would get these as your constants. So you'll have A0, A1, and A2 here. And then the bottom, we have A3, A4, and A5. If I scoot over, you can see, yep, this is your A5. So these would be your final solution if you were to use the quintic polynomial and solve your system of equations. Now in my ROS code here, I have a section on the joint space trajectory. So you have to first start up your hardware, which I already did. And then what you want to do is you could launch this file here, which I call the joint space trajectory.launch.py. So you want to set the initial position you want to have, and then, the target position is going to read the initial position based off of the joint states, and then you specify a duration. And then if we go ahead and run this, then we could see it move to our desired position. So you can see our graph running here in Plot Juggler, and you can see all the joints is nice and smooth. So in the previous video, we covered the joint space trajectory, but in this video, we're going to talk about the Cartesian space trajectory. By the end of this video, we'll see how to control the UR robot. You can follow along with the code and doc, link in the video description. If you want to see more behind the scene videos, make sure to join my membership, the Robotics Builders. So the key idea is you want your robot to move between 2 positions in space, and you would define this position using the transformation matrix, which we covered in our previous video. But essentially what you have is a rotation matrix, your 3x3 matrix, and you have your position vector, which is a 3x1 vector. So you have an initial and a final. This F here means final. So you want to see how to interpolate the position and orientation between these 2 points so that you can generate a smooth trajectory. So smoothness of the trajectory is guaranteed by imposing certain boundary conditions. So specifically, we want 0 velocity and acceleration at both ends, meaning the start and final position. So this gives us these equations here. So these are our boundary equations. So you can see we have our initial position, and then we have our velocity and acceleration. So we have the quintic polynomial. It's a 5th order polynomial here. So this is what's going to allow us to generate the 6 equations. Now to do interpolation in the linear space, so this is LERP linear interpolation. So we took our polynomial that we solved previously and we want to parameterize our equations. So we have our P0 and P final, which is our position vector for the start and final. And this is the equation that you use to interpolate it. So this is going to give us a smooth trajectory from the start to final position in the Cartesian space. Now, similarly for the orientation, we use SLURP, which is a spherical for the orientation, is a spherical interpolation. So we first want to find the relative orientation, which we call omega, taking the inverse of cosine for the product of the 2 quaternions. And then from there, we have our equation Q of t. So again, you could see our equation, the S that we used previously, which we define as our quintic polynomial. And we plug it into this equation with, signs in here that will eventually figure out the interpolation between the 2 angles. So again, we have our Q0 and Q final, which defines our initial and final orientation. So now that we have the quaternion as a function of time and the positions as a function of time, we could plug it back into our transformation matrix. So this part right here just means we're converting our quaternion to a rotation matrix. And once we have our transformation at each time step, then we could plug it back in here to our inverse kinematics to find our joint angles at every pose. But at least what this equation does, finding the key parts, which is the Q of t and P of t, which is the position and orientation, is that now that we have actual position and orientations that guarantee these velocity and acceleration conditions that we've imposed. So we're going to go ahead and start up our trajectory. So we have this command here that launches our trajectory that does the Cartesian space trajectory. So let's go ahead and run this. So you can see right here, we're just commanding the tool end to move from one pose to the other, and it generates pretty smooth trajectory in the joint space and Cartesian space. So in case you're confused about what smooth means, you could see this first graph here is a graph of our X, Y, and Z positions of the tool end. So you can see first it starts off flat, right? And then right here, it starts sloping down. So this part you can see is a gradual transition to the actual trajectory. You can see the same thing here, it slowly transitions down. So this is what's called smooth, because if you were to take the derivative of this, it's going to be differentiable and smooth. That's the definition. So you can also see that because there's no sudden jumps, because if you didn't do this whole, lerp and slurp, what's going to end up happening is, let's say your initial position was at 0 and then you commanded a new pose, then you're going to see a sudden jump down to a different position. Or you might, it's going to be a step change instead of a gradual change. So you could see it's being reflected in both the tool end position as well as the individual joints, because you could see also these joints are very smooth and gradual. So there's no sudden jumps for any of these trajectories. So previously we covered the Cartesian space trajectory. In this video, we'll talk about singularity. We'll cover some examples with a simple 2DOF robot and then end it with an example of the UR robot. You can follow along with my code and doc, link in the video description. If you want to see more behind the scene videos, make sure to join my membership, the Robotics Builders. So for a simple 2DOF robot, you can have a fully extended position and a folded position, both of which are at singular positions. Let's take a look at why it is. So singularity occurs when one or more degree of freedom is lost. So mathematically, you could confirm that by checking the columns of your Jacobian matrix. So if any of these columns are not linearly independent, then we know that it's at a singular position. So this is true for one or more sigma equal to 0, where n is greater than or equal to 6. So you could check this mathematically using the determinant J transpose. And when you do this, basically if one of these values is 0, then the determinant is going to be 0. So this means that the determinant of J is going to be 0 for n is less than 6. So depending on which case you have, you'll choose the right matrix to calculate it. And you can see right here, this is an example with the 2DOF. If we find the Jacobian, we have this as our final equation that calculates the Jacobian matrix. And if we calculate the determinant, we find this is the final expression. So at theta equals 2, meaning that the arm is fully extended. So in this case, we see the determinant is 0. And similarly, if it's folded up, we have the theta 2 equals to pi. And if we plug it in, we also see that the determinant is going to be 0. So mathematically, we've confirmed that both of these situations are at singularity. So first, we're going to launch our robot and then run the singularity node to check our singularity. So you can see right here, we already have our robot launched in RViz. So if I come back here, I could run my singularity node. And this is going to output the Jacobian as well as the determinant. So you can see that we have a determinant of 0, and this is our Jacobian matrix. Now, if we check for linear independence of the Jacobian matrix, we could see right away that the second, third, and fourth column, you could see that they are linearly dependent. So notice that all the ones show up in the fifth row, and then you could see that the first one is a non-zero value. This one right here, there's some tiny rounding errors, but you could treat them as zero. But basically, all three of these axes contribute to the same direction during that pose. So from here, we know that these three are linearly dependent and therefore confirms our assumption or calculation that we are currently in a singular position. And visually too, it makes sense because you can see joints 2, 3, and 4, they're all in the same plane. And when you rotate it, the tool end is going to move in the same direction. So that's another way to visually check that you are at a singularity. So previously we talked about singularity. In this video, we're going to talk about workspace. We'll cover an example with a 2DOF robot and the UR robot. You can follow along with my code and doc, link in the video description. If you want to see more behind the scene videos, make sure to join my membership, the Robotics Builders. Now, this right here is a workspace for a 2DOF robot. And the idea is this is the range of points that this robot can reach. So you typically can find this by sweeping the angles for theta 1 and theta 2, the two joints, and see all the points that it can reach. So for 2DOF, we're only dealing with positions, but the more general case is to have position and orientation. So the actual workspace that you get will depend on things like the number and types of joints that you have, the link lengths and offsets, and also the joint angle limits. Now, when we talk about workspaces, there's two types. So the first one is the reachable workspace, and the second type is the dexterous workspace. The first type, the reachable one, only requires at least one orientation at the specific point. But for the dexterous, it's going to be every orientation. So that's going to be the main difference. Now, the specific type of workspace you want to consider will depend on your application, because sometimes you might just care if the robot can get to that point, but other times you might care if it could get to that point and be at a certain orientation. Now, perhaps one of the easiest ways to figure out the workspace is to do a Monte Carlo sampling. So you want to sweep your angles between theta min and theta max randomly, and you could generate all the points of the tool end that it reaches, and that's going to be your workspace. You can also sweep it through very small increments, but Monte Carlo will be the most efficient way because you don't have to sample every single point. But if you want a workspace that's just granular enough, then really either way can work for you. So you can see right here, we're in ROS. We have a code here that could help us visualize our workspace. So we could go ahead and run one of these commands. There's a couple options to clip it because I want to just see half of it, because when you end up plotting the entire sphere, and it's pretty hard to see what's happening inside. So what people typically do is they like to do section view. So I'm mimicking the section view by cutting it in half. So you can see right here, I've set up my markers to subscribe to the topic workspace markers. And you can see this is basically the workspace, which is a sphere. And that agrees with some of our initial assumption of the robot. This is basically the 2DOF version, but extended to 3DOF, which is why we go from a circle to a sphere. There might be some space down here in the middle part that might not be reachable, but if you plot it in section views, you might be able to see that tiny space a little bit better. So previously we talked about how to find the workspace for your robot. In this video, we're going to find how to figure out your torques using the Newton-Euler method. By the end of this video, we'll see how we could simulate the torques using the UR robot. So the point of using the Newton-Euler dynamics is to figure out the torques required for each of the joints of your robot. So whether you're using this to size your actuators or you're doing this for some controller like gravity compensation, this is going to be very useful because that's how you know the exact torques your joints need. So the typical form of the equation is going to look like this right here. So T or tau is going to be mq double dot c q dot plus g. So these are different matrices. So M is going to be called your inertia matrix, sometimes also called the mass matrix. It's going to have the property of being positive definite. You also have the C matrix. This is called your Coriolis matrix, and the centrifugal. And then the G is your gravity vector. So this is the part that's affected only by the gravity component. So before you can solve the equations for Newton-Euler to get the final torque equation, you have to set up the initial conditions of your robot. So typically at the base frame, you're going to have a gravity vector and some fictitious upward acceleration. And you want to define your velocities and accelerations. So here we're going to assume these will be 0. So your angular velocity and your angular acceleration. And we also have our linear acceleration, which is going to be our gravity. It's just going to be 9.81. And then at the tip, this is the tool end of the frame. You want to assume if there's any forces. So for some of the basic cases, you could initially assume that there's no forces or torques applied at the tool end. But of course, you could complicate the situation and add a force if there is a force. So for Newton-Euler, there's going to be two parts to it. We have the outward iteration that will go from 0 to n-1. And then later, we're going to do an inward iteration that goes the opposite direction. So the point of the outward iteration is to start off with your angular velocity. So this is the equation. Then we calculate the angular acceleration. And this is the equation here. And finally, we have the linear acceleration of the frame origin. And you would use this equation. So the part that has the linear acceleration of the center mass for the link I+1, you're going to calculate it using this. And then we have the Newton's equation, which is going to get you the net force on the link I+1. So this is your force. And then finally, to get the torque, we use the Euler's equation, which is going to be this right here. So basically, the main goal of the first pass is to really get this Euler equation or the net torque on the link so that we could use it in this next pass. But first, you look at the transformation matrix, right? You could break up each transformation matrix that we talked about in the previous video into the rotation part and the position part. And this component right here, this is the direction of your axes. And you could pretty much get that from the last vector of your rotation matrix, which is this value right here. So once you get all that, you could also consider the inertia. So you could usually pull this straight from SolidWorks or any CAD model that you have. But if you have a point mass, you could simplify this and not have a matrix that represents your eye. So once you get all that, then you could finally move on to the inward iteration, which will go from n to 1. And from here, you could take the things that we calculated, right? So we calculated the force. You would plug it in this equation to get the force exerted on link I by link I minus I. And then from there, you could calculate the moment exerted on the links. This is the little n. And we use the results that we got previously, which is the capital N. And finally, once you do all that, then this is a final part that you really need, which is ultimately the torque that's at each joint. So this is going to be n transpose the direction of your axes. So when you repeat the process for each joint, you're going to assemble this final matrix that's your tau here. And you have tau 1 up to tau n, where n is the number of joints that you have. And then you could break it up into this matrix form here. So this is more common when you're dealing with different types of controllers where you want to actually pull out the different inertia, the Coriolis centrifugal, or the gravity matrix, because you might use some of these matrix in your block diagram where you're designing your feedback loop controllers for like gravity compensation, for example. And there's a couple of tricks too in terms of how to isolate these matrix. So to get G, you could set Q dot and Q double dot to be 0. To get M, you could set Q dot equals to 0 and then set Q double dot equals EI for each of the columns. And then for C, you could subtract G and MQ double dot to get the final result. Now, the best way to understand all this is with an example. So we'll be covering a 2DOF robot example here. And you can see right off the bat, we have our rotation matrices, which we covered in our previous videos where we covered the transformation matrix. So we're just pulling the results straight from there. So here we have our rotation matrices, just rotation about the z-axis, right? And then we have our position and center of mass vector. So because we're assuming point mass assumption, it makes it a little bit easier. So that's why our position vectors and our center of mass is going to be the same because it's at the location of the joints. Otherwise, normally it might be somewhere in between. So you'll have to figure out from your CAD model or whatever method you're using it to figure that out. And for our inertia tensor, again, we have some simplifications here. So because we have point mass, our I matrix is going to be 0. And for our initial conditions, we have zeros for the angular velocity and acceleration, but for the linear acceleration, we have gravity. So first we do the forward pass for link 1, right? So we have our angular velocity, which we use this equation. We have 0 for our initial condition, and then we add this component, which is our velocity. We only have it at theta dot. So we have theta dot as our final angular velocity. For our angular acceleration, we plug it into this equation, and we're left with only the component at the joint, which is theta 1 double dot. Now we go on to the linear acceleration of the frame. So notice that the initial position is going to be 0 here. So we plug it in here. We have our rotation matrix and our gravity. Then we get S1G, C1G. And then for the center of mass acceleration, we use this equation. We plug in the different components, and then our final result is going to be this matrix right here. Now for F, we take our result from previous, plug it in, we get this matrix here, and for N, we have 0. Now for forward pass for link 2, we go through the angular velocity, we plug it into this equation. Now we have theta 1 dot and theta 2 dot show up. For the angular acceleration, we have theta 1 double dot, theta 2 double dot. Now for the linear acceleration part, we have this equation which we plug in. The final result is going to be this matrix here. And then the center mass acceleration and Newton-Euler for link 2 will follow the same patterns. Now we could go on to the backward pass. We start off with link 2. We want to calculate F. We take this equation. We get this as our result. And then for N2, we take this equation, and then this will be the final result. So when you take all of that, we could finally calculate tau of 2, and it's going to be this equation here. Then if you substitute everything, then you'll see that this is the final expression for tau 2. Now for link 1, again, we do the same process, little f here, little n, plug it in. And then once you plug everything in, you're going to get tau 1 here. Then now this is where you could construct it to the inertia matrix M, your Coriolis, and also your gravity. Then you can use the result like this in its final form. Now we can analyze a few cases to see if our equation makes sense. So we could take a look at the static gravity case. So this is going to be where the velocity and accelerations are 0, and we're checking for the g or the gravity component. So if we do that, we see this is our equation for tau 1 and this is for tau 2. So in the horizontal configuration, we have our thetas equal to 0, which means that our cosine component is going to be 1. And if we do that, we see this is our expression. So we have m1lg. So this is the equation for weight, right? Weight equals mass times g, but this is torque, so you have some distance. So basically this is saying m1g is your weight vector times L1. So that part makes sense for tau 1. And then you have a second component here, right? You have m2 times L1 plus L2. So it's saying that mass 2 is at a distance of L1 plus L2 away from the first joint. So this is your second W. So we could think of this as W2, W1. So this is your W1 component and your W2 component. And then because it's torque, so you times the 2 lanes. So this tau 1 makes sense conceptually. And tau 2 is going to be relative to this frame. So what is the weight times the distance or the torque that you see from the second joint is going to be m2 times g, which is the weight of this relative to the second frame times your length L2. So this results makes sense as well. So this is a quick way to do a sanity check to see if your results make sense. You go through the same process for the different components, but here we're just analyzing the static case. Now we have an example here in ROS 2. We're going to run our UR robot, and the program we're going to be running is going to be the UR Kinematics Newton-Euler Dynamics. So this is going to show us move the robot from a straight up position, which is how the robot is initially configured, go to elbow up pointing down position, and then draw a circle. And then during this motion, it's going to plot the torques that it's using to generate that motion. So you can see right here as it's drawing the circle, the torques are being plotted. Most of the torque that's being applied that varies is going to be J2 because you could see that it's moving closer and away from the base. So that's why J2 sees most of the torque difference. Some of the other torques, because of how slow it's moving, is just basically trying to maintain its current position so you don't see too much change in those torques. So previously we covered the Newton-Euler dynamics. In this video, we'll cover the Lagrangian dynamics. We will start off with a 2DOF robot example and then end it with the UR robot simulation in ROS. You can follow along with the code and doc, link in the video description. If you want to see more behind-the-scenes videos, make sure to join my membership, the Robotics Builders. So the core difference with the Lagrangian is that we're using energy, specifically the kinetic and potential energy, to figure out the torques required at each joint. So this L here is the Lagrangian symbol, and we have the kinetic energy minus the potential energy. So to find the torque, you actually have to find the partial derivatives of the Lagrangian. And you want to find the difference between the two. And this part for the kinetic energy, you need to take the delta d of dt. So for the kinetic energy, we break it down into the linear part and rotational part. So this is very similar to the form of 1/2 mv squared, but in matrix form, we have P transpose P. These P's are the position vectors to the center of mass. So this is why there's a Ci here. And you can see we could obtain this by using the column of the Jacobian that corresponds to that link multiplied by Q dot, because we know that we could take the rotational part of each joint and convert it to the linear velocity by the definition of the Jacobian. And same thing for the rotational part. We take the rotational part of the Jacobian matrix, multiply it by Q dot, and then we get our omegas. So the total kinetic energy can also be written in this form with the mass matrix. So you can see we have Q dot transpose M Q dot. And if we expand it out, we see the terms that we showed previously on top. We have the linear and rotational part. So you just sum it up for all the links, then you'll have your mass matrix here. Okay, so let's take a look at a 2DOF robot example. So we have our two joints here, theta 1 and theta 2. And if we take a look at the first step, we have the position of our masses. So we have L1C1, L1S1. So that's for P1, and P2 is just an extension of that. We have our velocities, so P1 dot and P2 dot. Then we could calculate our kinetic energy using the formula we saw previously, which is the form of 1/2 mv squared. Here we're using P dot 1. And the final equation, once you plug everything in, is 1/2 m1 L1 squared theta dot 1 squared. Now for link 2, we take P2 dot, square it, and then we're going to get this expression here, plug it into the 1/2 m2 P2 dot squared, and then that's going to be your kinetic energy. So to find the mass matrix, we combine everything and then split it up, put it in each of the components of the matrix. This is going to be your final solution. So moving on to the next step, step 4 is the potential energy. So the core idea of the potential energy is mgh. So this is mg and this is the h part, but we're using sine and cosine to figure out the right vertical component of it. So this is for m1. M2 follows a similar structure. We have the different components for the two linkages. And if you simplify and add everything up, you get this as your final expression. So we can move on to the definition of Lagrangian now is K minus V. So if we see step 6, this is where we find the partial L, partial theta 1 dot. And if you plug in everything and go through the process, then you could see this is our final equation for tau 1. And you do the same thing for theta 2. So we have the equation for Lagrangian. We take the partial derivative, and we need to take d dt. And then this is a partial L, partial theta 2. Then finally you substitute in and we get tau 2. Now we get our final equation of motion. We could break it up into the three main matrix, the M, C, and G, and you could see these are the final results for the three matrix. So here we are in ROS. We're gonna set up our UR robot to run the Lagrangian dynamics using this command right here. So it's gonna go into the elbow up position with the tool end pointing down and draw a circle. And while it's drawing the circle, we could visualize the torques in real time. So it'll be a pretty good exercise if you want to compare the results of the Lagrangian with our Newton-Euler dynamics, which we covered in our previous video, and compare the results, which should match between the two methods.